In this lesson, we will study both linear speed and angular speed. Let's start with the definition. Suppose that point P moves at a constant speed along a circle of radius r and center O. The measure of how fast the position of P is changing is the linear speed. So you got this P, this point P here, and it is moving at a constant speed along a circle, right? And this circle has center O and radius r, and the speed at which the point P is changing is the linear speed. And so if the letter V represents linear speed, then we have this formula. Speed is equal to distance over time, right? We know that formula already. Speed is equal to distance over time. So V, the linear speed, is equal to the distance. S is the arc that is traced, by point P. So S stands for distance over time. You're going to want to remember this formula. Notice that it's similar to, a lot of people remember distance is equal to rate times time. A lot of times rate is the same thing as speed, right? And so if you isolate this formula here that you know of already, if you isolate it for speed or the rate, you would divide both sides by t, wouldn't you? And you would get that the rate or the speed is equal to the distance over time. All right, so that's exactly where this comes from. But in this context, we use the letter V to represent the speed, the linear speed at which point P is changing. So it's similar. See, the rate or the speed is equal to distance over time. The speed, the linear speed, is equal to distance over time. In this context, distance is s, the arc that is traced by point P. So this formula, speed is equal to distance divided by time, is very similar to this speed is equal to distance divided by time. I just wanted you to see that you've seen a formula like this before. The variables are different. The letters that are being used from our alphabet are different for speed and for distance. But it's very similar. So you're going to want to make sure that you have this highlighted, everybody, in your notes. You're going to want to use this formula a lot whenever you're trying to find linear speed. All right? Now we also have something called angular speed. So notice that as point P moves along the circle, this ray right here, OP, rotates around the origin. As point P moves, this ray is rotating around the origin. And because ray OP is the terminal side of this angle POB, the measure of the angle changes as point P moves along the circle. So as point P moves this way around the circle, this angle POB is opening more as well, changing its measure. The measure of how fast angle POB is changing is its angular speed. Okay, remember, linear speed is the speed at which point P is moving. Angular speed is how fast the angle POB is changing. Here's our formula for angular speed. Now, this is the Greek letter omega. Omega is equal to theta divided by t. Now, remember here, theta is in radians. Theta is in radians. Now, here, theta is the measure of angle POB at time t, right? At whatever time we're considering, all right? Now, again, remember that theta is in radians, okay? All right, let's box this. This is a formula that you're going to want to be very, very, very familiar with, all right? So you got a formula for linear speed, which is the speed at which point P is changing. And you got a formula for angular speed for how fast the measure of angle POB is changing. I want to show you an alternative formula. So we start here with the formula for the linear speed. Remember, V stands for linear speed, S stands for distance, which is basically the length of the arc that is traced by that point P moving along the circle, and T stands for time. But we've learned in earlier lessons that S, that arc length, is the product of the radius of the circle and the radian measure of angle theta. And so we have that V then can be rewritten as R theta over T. Okay, now this can be rewritten as R times theta over T. So watch this. Linear speed can be also written as R times omega. This here, theta divided by T, is what omega is. So this here, folks, is an alternative formula for linear speed. This formula for linear speed differs from this one. This linear speed is the quotient of the distance and the time. This one is the product of the radius of the circle and omega, which is the angular speed. So before we look at a few examples, I wanted to kind of summarize our formulas. This is arc length. S stands for arc length. R stands for the radius of the circle. Theta stands for the radian measure of your angle. Let's see. V stands for linear speed. We already said what S is. T is time. And this is omega. This is not W. This is omega, which stands for angular speed. And I think we covered it all. That's what each one of these letters represent. So you have a formula here for arc length. You have a formula here for linear speed, an alternative formula for linear speed, and then you have the formula for angular speed. All right, in this example, there's going to be 3 different parts. So I only have the first part so far written. All right, here we go. Suppose that P, point P, is on a circle with radius 15 inches, and ray OP is rotating with angular speed, pi over 12 radian per second. Okay, keep this in mind. They've given you R, right here, the radius, and they have given you omega, okay, which is the angular speed. In this first part, they want you to find the angle generated by point P in 10 seconds. Oh, notice they also have given you time. All right, they want you to find theta. They want you to find theta. Now, we have this formula that the angular speed is equal to theta over T. Now, in this is the formula for angular speed. They've given you the angular speed. They've given you time. What they have not given you is theta. That's what you need to find. So what I'm going to do is I am going to I am going to alter this formula by multiplying both sides by T, and I will get, alternatively, that theta is equal to the angular speed times time. Okay, everybody? So that means theta will be equal to pi over 12 radians times 10 seconds. So theta, right? And this is pi over 12 radians per second times 10 seconds. Actually, I think it would be a good idea if I go back here. Let me see if I can go back. And actually, let me come over here, leave lots of room. Theta is equal to pi over 12 radians per second, right? That's omega, times 10 seconds, right? That's time. What I wanted to really show you is I wanted to convince you that the seconds are gone, right? They get canceled out. The GCF between 10 and 12 is 2. 2 goes into 10 5 times, and 2 goes into 12 6 times. So then the radian measure of theta is just 5 pi over 6 radians. Okay? All right, so there's the answer for the first part. This is the angle. Let's be very clear as to what we found. We found the angle that is generated by point P in 10 seconds. So as 10 seconds have passed, as soon as 10 seconds have transpired, This is the angle that is generated by point P moving along the circle. All right, let's go for the second part now. Now the second part is find the distance traveled by P along the circle in, that's the word, that should be in 10 seconds. Let me change that for us. Now, when they say find the distance, right, that means you are looking for S. Remember, S is representative of the distance. Now, the formula that we could use here is S is equal to the radius times the radian measure of angle theta. Now, we are given the radius is 15 inches, and we are given the radian measure of angle theta that is generated in 10 seconds. That's what we just figured out in the previous part. So the radian measure is 5 pi over 6, like that. So let's just do some arithmetic now. The GCF between 15 and 6 is 3. So 3 goes into 6 twice. 3 goes into 15 5 times. And so S then is equal to 25 pi over 2 inches, right? Which is 12.5 pi inches. Now this is an exact answer because I'm leaving it in terms of pi, right? If I punch this into the calculator and press pi, as soon as I press pi, it's no longer an exact answer, it's an approximation. So this is my exact answer. This is how many inches that is traced out by point P in 10 seconds. Cool, let's go to the last part. Now the last part is find the linear speed, that's V, right? Find the linear speed of P in inches per second, in inches per second. All right, very good. Now we have this formula that V is equal to S divided by T. Now, we know S, we just figured it out. The distance that is traced out, right, by point P was 25 pi over 2, right, inches. That's S. And that happens in 10 seconds, right? Do you remember that being the time? Right? In the previous problem, it said that point P, or we concluded that point P has traced out this distance and the time was 10 seconds. So we just have some arithmetic to do here. So then this is 25 halves pi inches times 1 over 10 seconds, right? Okay. So let us divide here. The GCF between 10 and 25 is 5. 5 goes into 10 twice. 5 goes into 25 5 times. And so if I can move up here, let's see. All right, so then V is equal to 5 pi over 4 inches per second. That is the linear speed of point P, okay? The linear speed. Very good, everybody. That was fun. Check out this example. A belt runs a pulley. Here's the belt, right, that I've drawn in red. Very fancy. A belt runs a pulley of radius 5 inches at 120 revolutions per minute. Remember, one revolution is one complete time around, okay? One complete time around. So you can also say rotations, all right? So 120 revolutions per minute. Now, the first question says, or the first part, find the angular speed of the pulley in radians per second. Find the angular speed of the pulley in radians per second. Find the speed at which the angle is changing. All right, to get this started, we're going to set up a ratio. 120 revolutions per minute. Okay, and they want the angular speed of the pulley in radians per second. So what we're going to do is we're going to multiply by some unit fractions. Since they want radians per second, remember that instead of revolutions, I want radians. And so the first thing I'm going to do is convert this to radians. So I know that I want the revolutions to cancel. So I'm going to put one revolution down here so that these revolutions will cancel out. And one revolution is 2 pi radians. This is a unit fraction. 2 pi is 1 revolution. So this is equivalent to 1. It's a unit fraction. Times, now I not only want it in terms of radians, I want it in terms of seconds. So we know that every 60 seconds is 1 minute. So I'm going to multiply by 1 minute over 60 seconds. And the reason why the minutes is up here is so that it divides out with this minute here. All right, let's start dividing out, everybody. So revolution and revolution are divided out. Minutes and minutes are divided out. And what do you want to do here? How about 60 goes into 120 exactly twice? So here, when you multiply what's left over here, you can see, can I move up a little bit here? You can see that you're left with 2 times 2 pi, which is 4 pi, radians per second. Let's actually write it out. Let's be more precise. 4 pi, I'm going to write this out right here for us, guys. Radians per second. Okay. All right. So this is the angular speed for this context. All right. Cool. Let's do the second part of this problem. The second part says find the linear speed. Remember, linear speed, just as a reminder, is v, right? Find the linear speed of the belt in centimeters per second. Now, remember this formula that the linear speed is equal to the product of the radius and omega, which is the angular speed that you and I just found in the previous part. So therefore, the linear speed is equal to the product of 5 inches times 4 pi radians per second. So then here, we can just multiply, and we can find that the linear speed in terms of pi, so an exact answer, would be 20 pi inches per second. Now, that's an exact answer, everybody. I'm going to box that right now. I'll go ahead and box that. If you want an approximation, then you would have to punch pi into your calculator. And if you do that, you should get that the linear speed is approximately 63 inches per second, right? Which makes sense because pi is about 3.14, so about 3, and 3 times 20 is 60, so we're in the ballpark. That's an approximation, though. Okay, this is approximation. All right, let's check out this problem, which is the last one, and it's probably my favorite. A satellite traveling in a circular orbit, right, 1,800 kilometers above the surface of Earth takes 2.5 hours to make an orbit, all right, to make one complete rotation, one complete revolution. One complete rotation takes 2.5 hours. Now, the radius of Earth is approximately 6,400 kilometers, okay? Approximate the linear speed of the satellite in kilometers per hour. Approximate the linear speed, now remember linear speed is v, of the satellite in kilometers per hour. All right, the first thing I want to notice here, or notate, is that I'm thinking about using this formula, that v, the linear speed, is equal to the product of the radius, which they've given me, and omega, the angular speed. So what comes to mind right away is I know the radius, and actually the radius, you got to be careful here because it's not just going to be the radius of Earth, right? Because the satellite is 1,800 kilometers plus 6,400 kilometers more, right? So it's orbiting around here, and the radius is the sum. The total radius is the sum of this distance and this distance. But you know what? So I can easily find that 1,800 plus 6,400 would be the total radius here. But what is not completely clear is what about the angular speed? Because they don't give that to me. So let's walk through this. We need to calculate r, the total radius. We can do that right now. And we need omega. And if we can find both of these two things, we'll multiply them together to find the linear speed. So that's our task. All right, here we go. So if we add 1,800 and 6,400 kilometers together, we'll get the total number of kilometers for the radius. So you're going to want to make sure you use this value for r, okay? I'm going to just kind of like highlight it. I'm not going to box it because it's not my final answer, of course, but I just want to highlight it because this is the r value that we're going to be using for this formula. Now, I need omega. Now, let me move this up a little bit. Now, omega, don't forget, omega stands for, or omega represents angular speed. Angular speed. Now, they told us in this problem that it takes 2.5 hours to make one complete orbit. Do you remember this formula for angular speed, theta divided by t? And we know that it takes 2.5 hours, right? So that's your time. And the angle theta would be 2 pi. Why? Well, because it says it takes 2.5 hours to make one complete orbit, and one time around is 2 pi. So if I were to divide both of these, I will get, let's see, if it helps at all, I'm not sure if it does, but I'm not going to use a calculator. I'm going to write 2.5 as 5 halves, right? This is per hour. Oops. Let's see if I can write that nicer. All right, so anyway, this is 2 pi radians times 2/5, right? And then we have hours. All right, so anyway, we can see that omega, the angular speed, is 4 pi over 5 radians per hour. All right, per hour. All right, everybody. Now that I know, let me highlight this for us. Now that I know my angular speed and my radius, I'll take these two quantities, plug them into this formula to find my linear speed. Okay? Let me move this up. All right, so here we go. V, the linear speed, is the radius times the angular speed. And we know that the total radius is 8,200 kilometers. And we now know that the angular speed, we had to find it, is 4 pi over 5 radians per hour. Okay, everybody? Again, I'm not going to use a calculator. You can if you'd like. But I noticed that, let's see. I noticed that 5 divides into 8,200. Let's see. It'll be 1,060. Let's see. 5 goes into 8 one time. You'll have 32. I'm doing all this in my head. 5 times 6 is 30. And then a 20. So this should be a 4 here and a 0. All right. And so what I'll do now is just multiply 1,640 by 4. Okay. And so 4 times 0 is 0. Let's write that down. 4 times 4 is 16. So I'll write a 6 and carry the 1. 4 times 6 is 24, plus the 1 is 25. I'll carry the 2. 4 times 1 is 4, plus the 2 is 6 pi radians per hour. 6,560 pi radians per hour. Okay, everybody? Now, if you punch into your calculator, pi, right? And let's see, how many significant digits do we have in this problem? I'm going to have to scroll all the way back up to find the given information. Where is it? Here it is. Look at the given information, everybody. How many significant digits in this number, 1800? 2. In this number, 2.5, 2 significant digits. In this number, 6400, 2 significant digits. So what I'm going to do now at the very end of this problem here is I am going to multiply 6,560 by pi, but make sure that you punch in the button pi on your calculator. Don't use 3.14. And round to 2 significant digits. And you should get approximately 21,000 kilometers per hour. You know what? I just noticed right here, a little mistake here. I see kilometers. I forgot to bring down that unit right here. It should be pi kilometers per hour. Here, I'll add it really quickly. Kilometers per hour. All right, so this is your final answer. It is an approximation, about 21,000 kilometers per hour. So in order to find the linear speed, you and I needed to find the total radius, and we needed to find the angular measure. Once we found those two things, multiply them together, do the arithmetic, and you find the linear speed. Now the last part of this says approximate the distance. Wait, stop right there. Remember that distance is what S represents. So you have to approximate the distance that the satellite travels in 3.5 hours. Okay, we just found linear speed, everybody. We just found linear speed. And they want to know S, and they've given us T. We know what V is, V, the linear speed. All right, so I'm thinking about this formula. How about you? I'm thinking about V is equal to S over T, right? The linear speed is equal to the quotient of the distance and time. I know time. We just figured out V, so we can plug in these two pieces of information and solve for S. First of all, though, let us rewrite this. Multiplying both sides by T, you would find that S, the distance, is equal to the product of the linear speed and time T. All right, cool. So let's use it. So the distance will be equal to linear speed. Now, we found an exact answer for linear speed a second ago, or a minute ago. We found it to be 6,560 pi kilometers, right? Per hour. Let me write it, save space here. Per hour. That was the exact value. That was the exact value for linear speed a second ago, times 3.5 hours. That's time. Notice that your hours cancel, right? So we're not talking about hours, of course. We're talking about distance. So our total distance will be, or our distance will be in terms of kilometers. Okay? So in my calculator, I am going to multiply 6,560 by pi, okay, by pi, and then I'll multiply that by 3.5. So three different numbers, 6,560 times pi times 3.5. And don't forget, we are rounding to only 2 significant digits. First of all, I'll give an exact answer. In terms of pi, all I'm going to do is 6,560 times 3.5, and that will give me 22,960 pi kilometers. That's an exact answer, ladies and gentlemen. An exact answer. Again, I did that by multiplying 6,560 by 3.5. Leave pi in your problem. That's in terms of pi. That's an exact answer. Now, an approximation Now, they never said find an exact answer, so I feel a little strange boxing that. Maybe I shouldn't box it. But anyway, let's keep going. So S is approximately equal to, now this is when you're going to take this number and multiply it by pi. 22,960 multiplied by pi and round to two significant digits would be approximately equal to 72,000 kilometers. Okay, this is the real answer because they're the ones that said approximate the answer, and this is the approximation. All right, everybody, I hope you enjoyed this lesson. I really, really enjoyed it. I think these applications are super cool. All right, catch you later.